Hey there, kiddos. Hope everyone is well. What I'd like to do is go over some of the word problems from our practice test today. So I'm going to try to go through this quickly. You can, of course, pause at your house or wherever you're watching, on the bus, right before the test, as you're walking to class, wherever. So let's take a look at the first one. First, a long-distance runner running at 9 miles per hour. I think they get tired, they run out of steam, they turn around and heads back along the same route, a little bit slower this time, 6 miles per hour. Although that's, for me, 6 miles per hour is pretty fast. If the whole race took 2.5 hours, how long did they travel, the runner? Okay, so here's what's happening. The runner is starting here, going some distance, stopping, and running back. Okay, so what we have is we have the rate for each trek. We have the total time, and we know that distance equals rate times time. Okay, so here's my framing, right? I'm going to first frame it, and basically what we have is the distance going there is the same as the distance back. Does that make sense? Right, so we kind of run to some point, stop, and in this case we run right back. So each of the distance forwards and backwards is the same, right? So there's my framing, okay? Now in the context of this problem, as we have been doing, we want to kind of, well, how do you rewrite, how do you get more particular if we talk about distance, right? Well, distance is rate times time, and we have some information about the rates, 9 miles per hour, 6 miles per hour, and we have some information about time, the total time, right? So here we go. So the distance there, I'm just going to replace that with rate times time, right? And the runner at first is running at a rate of 9 miles per hour, right? So I'm replacing distance with rate times time, rate times time, right? And that distance back, rate times time, right? So I'm just going to replace the rate with 9, and then I'm not quite sure about time yet, so I'm going to leave that for now. So the rate going there is 9 miles per hour, and I know the rate going back, this particular rate right here, is 6 miles per hour, a little slower, right? But the question is, what are the times? What are the times? Now, I know the whole race took 2.5 hours, right? So, if I run t hours to get there, then I therefore will run 2.5 minus t hours to return, okay? So what I've done is I let t be the number of hours. Right. So rate 9 miles per hour times t hours is equal to the rate coming back. 6 miles per hour times, well, the time coming back, if I run 1 hour there, then I run 1.5 hours coming back. If I run half hour going there, I run 2 hours coming back. If I run t hours going there, I run 2.5 minus t going back, right? Because I know the total time, 2.5 hours. Right? And so now it just becomes a case where I solve. And I'll leave the solving piece up to you, right? So now you can solve. There's our setup. Now you can solve, right? If you have questions, let me know. But in the interest of time, we're just going to set it up. All right, there's my setup. Okay. All right, next problem. Let's go to a coin or ticket or whatever problem. Now, for these types of problems, you basically have two choices, right? You either have quarters and dimes, or you have good tickets and bad tickets, you have hot dogs and hamburgers, and each of those choices there's an appropriate cost, right? So for this particular, I have the gross for One Direction concert, which was pretty sick, and I know that the good tickets are 48, the bad tickets 26, and I know how many total tickets, right? So here we go, I'm going to frame it. I'm going to start by framing it. So basically I want to say the money I make for bad tickets plus the money I made for good tickets, or from, I guess, is equal to the gross, 166,530. Right? That makes sense? So there's my frame. Okay, so One Direction or whomever, right? They made some money from selling bad tickets, not so good tickets. They made some money from selling good tickets, and that totaled $166,530. Okay, there's my frame. Now I just want to get a little particular, right? So how can I say more specifically or quantify how much money I made for bad tickets, right? Well, bad tickets, kind of like I did in the last problem, how do I reframe distance? And I decided it was rate times time. So in this problem, I want to say, well, how can I quantify money I made from bad tickets? And you know what? That's just going to be cost per ticket times number of tickets. All right? Agree? Wouldn't you say that money made from selling bad tickets is the number of bad tickets times the cost per ticket? Sure. Right? So I'm going to replace that with both. And I mean by number of tickets sold, right? Plus cost times number of those tickets is 166,530. Right? Now I just need to quantify. Right? I need to get more particular, right? So in order to do so, I'm going to say, okay, well, let's let X be number of bad tickets sold. Right? And now that's important because now I can say, okay, therefore, the cost of those bad tickets, right? I know they're 26 a pop. I'll get rid of the dollar sign, times the number of bad tickets, plus, well, now I can say the cost of the good tickets, right? How much money we make from good tickets? Well, that's $48 per ticket. And just like I did in the previous example, these are the total tickets, 5,250, right? So if I sold X number of bad tickets, then, therefore, we sold 5,250 minus X good tickets, right? Just like in the previous example, if it's 2.5 hour trip, then it's T hours going there and 2.5 minus T hours coming back, right? So you kind of take the total and you parse that up into two pieces, T and 2.5 minus T, just like I do in this problem, right? Oh, wow, right? 5,250 total tickets. So I split that up into X for bad tickets, therefore 5,250 minus X for the good tickets. And of course, there's my total cost. Okay. Again, here's your setup. And I'll leave the solving up to you. Don't forget to distribute this 48. Okay, 26X plus 48 times the quantity, 5,250 minus X, equals a total gross ticket sales. Okay, and I'll leave that to you to finish up. Moving on. This one is in slope-intercept form, and let's see if we can pick that up. Okay. Suppose a total Prius costs $22,500 to purchase, right? That's kind of your startup cost. And then an additional $80 per month for gas. Now that word per should kind of give me a good hint that 80 is the slope, right? That's what slope is, rate of change, right? What will over the years? So here's my cost function. The cost, I'll just type it out at first, over X months, cost of my Prius for X months equals the purchase price, right, which is $22,500 plus $80 per month. Now, if it's X months, that just means 80X, right? There's your slope, 80. Here's your y-intercept or startup cost. And now I'm just I can call it C of X, or if you don't like that notation, you can just call that Y. Okay? So let Y be the cost for the Prius. And that's over X months. Right? This is the number of months. This is the according cost. Okay? So what will the cost of the Prius be over 3 years? So for 3 years, I plug in 36 because that's 36 months for X, right? So therefore the cost for 3 years is the cost of 36 months, which is 22,500 plus 80 times, plug that 36 in. All right, and I'll leave that up to you to calculate. Okay. Part B, well, when will the total Prius cost be $30,000, right? So when will the cost be $30,000? So now I'm going to plug $30,000 here, right? right? So that's plugging in 30,000 not for X but for Y. So 30,000 cost equals 22 the startup cost plus $80 a month for how many months, right? For how many months? And I can solve for X, or you can do that at home. Okay. So there's your slope-intercept form. 80, of course, is your slope. Here's your rate of change, $80 per month. And this is your startup cost, your cost-intercept, or your y-intercept. Okay. Last problem. Going fast. Here's many of the problems we've done. I've given you 2 points, right? So here's such an example. So basically what we have is we have a 19-pound bike, gives us that height of a jump, versus a 21-pound bike is heavier. It's not going to jump as high, right? So if you're into BMX, X Games, all that stuff, here you go, right? So I need to find a linear function, right? So let's do that, right? So I'm using the points 19 pounds, and then height jumped. That's kind of the way I'm setting it up, right? So the pounds is 19, and the according height is 1035. And of course, that's in, for this problem, feet. And then the other point that I have is 21 pounds. And that particular 21-pound bike jumped an average of 10.11 feet, right? So there are my 2 points, right? So what I need to do now is I need to calculate the slope, right? And in order to calculate the slope, I need to use change of height over change in pounds, right? So the change in height is, and I'll do this one out, 10.35. And I'm finding the slope because I need that to find the equation of the line. 10.11. I could have done this in my head. Oh well. Might as well use that thing up. So it's 0.24. Now I want to divide that, the change in height, by the change in pounds. So I'm going to divide that by really 21 minus 19, which is 2. Right? So 0.12 is my slope. Okay, so the slope, or M, is 0.12. Now it has meaning here, and it's change of height, so feet, per change of quote-unquote X, which is pound. Right? Which means that in theory, based on these 2 points with a line between them, for each additional pound of bike, oopsie, that should be negative, sorry. I lose 0.12 feet of height. Okay? So that's what it means, right? Now let's use that to find the equation of the line, right? So let's find the equation of the line. There's my slope. Bam. Let's now use that to find the equation of the line. So I like to use y minus y1 equals m times the quantity x minus x1. And I like that. It's called slope, which I know is negative 0.12. Point goes here, form, point slope. So I'm just going to take one of these 2 points and plug it in for x1, 19, and then plug the y value for y1, 10.35. Okay? Now that looks kind of messy, so I'm going to clean it up, right? That is truly the equation of the line I'm looking for between these 2 points. But that said, most people don't like to keep it in that form. So what I'm going to do is I'm going to distribute the negative 0.12. And then I'm going to continue to clean it up. Negative 0.12x. And then distribute again the negative 0.12 times really negative 19. Of course, the 2 negatives positive. And I get 2.28 plus. Right, now I'm going to add this 10.35. And that's going to give me my magical y-intercept. Okay, so what I'm really doing is y equals negative 0.12x plus 12.63. Okay, that is my linear function that runs through those 2 points. Here's my slope. Here's my quote-unquote y-intercept. In this case, that would indicate the weight for jumping 0 feet. Okay. Now I'm going to use that to answer the following questions. If 17.5-pound bike is engineered, what would the height, right? Well, remember, x is the pounds, y is the height, right? So to answer that question, the height, which is y, is equal to negative 0.12x. And in this case, x is 17.5 plus 12.63. All right, I'll let you do that. And of course, that's a number of feet, that jump you would expect that bike to jump. And moving down, oh, that's it. How about that? Okay. So there you go. I try to go through that quickly. Please feel free to pause, come in with questions, or ask me questions. Good luck studying. Bye-bye.